In fact, I have a thought puzzle that I'll bring up shortly that is exactly that concept. Lesson 2. So far we've learned Newton's laws to describe how things move. And we got to give Mr. Newton full credit because he was envisioning what outer space would be like, especially with Newton's first law, at a time when we hadn't even invented hot air balloons or anything. He was imagining, okay, there's got to be a situation out there where there are no forces acting on an object. It's going to keep going in a straight line at a steady speed. It's not going to stop on its own. Aristotle was wrong. Full cred for that. Then we had Newton's third law, forces come in pairs, but now we're going to start to use the equation a lot more. F equals what? Ma. And sometimes we'll use Chiana's law modified. A equals F over M. A spacecraft has a mass of 3.25 times 10 to the fourth kilograms. By the way, what are the proper units for mass? So when you see kilograms, you know that's going to be M, a mass, right? It can exert a thrust force of 7.25 times 10 to the fourth newtons. We're talking about outer space now. Cool. Riley, what's A want me to find? I might be tempted, don't write this down, I might start going to myself, well, A equals question mark, what's VI? What's VI? I don't see a VI or a VF or a D or, wait a minute, what's kilograms, Riley, a measure of? What's newtons a measure of? Chiana's law. I would probably start out by thinking to myself, F equals what, MA. Chiana, get the A by itself, please. Divide by M, divide by M. You're going to see that acceleration is an important enough concept that we're going to have many different ways to find it. And so I use what information the question gave me as I'm reading. It already guides my thoughts into a certain direction. 7.25 times 10 to the fourth divided by 3.25 times 10 to the fourth. Time to get my trusty calculator out. 7.25 times 10 to the fourth divided by 3.25, scientific notation button 4. And I get 2.23. Anybody else? Acceleration, units, meters per second squared. Mr. Dewick, did somebody lose a half mark on the test just because they forgot to put units on one question? Maybe. I know a few people forgot to put units on a question. I took a half mark off. Good habit before you hand any test in is to do what? Go through all the written section and make sure each question has units. All right, let's keep going here. So we're accelerating at 2.23 meters per second squared. Is that big? That's kind of meh. You'd feel it, but you'd pretty quickly ignore it. Suppose the spacecraft maintains this acceleration for 12 minutes. Nice try. I don't do physics with minutes. How do I convert minutes to seconds? Okay, so what is 12 times 60? 720? Yep. I'm going to cross out the 12 minutes and put a 720 seconds right there so I don't make that silly mistake. Before turning off the engine, and if its initial velocity was 5.6 times 10 to the 3 meters per second, what will the final velocity of the spacecraft be? Oh, nice little bit of review. Looks like this is asking me to find VF. Looks like VI was 5.6 times 10 to the 3. Looks like T is 720. That's only 2 things. I need 3 things to find the fourth. Yep. So now that we've done one actual physics unit, as far as I'm concerned now, it's fair game for me to expect you to use an answer to find another answer. Okay? I'm going to write 2.23, but of course Aiden knows I'm going to use my answer button. I didn't tell you to get your green sheet out. It's VF equals VI plus AT, yes? I'm going from memory, but I'm pretty sure that's what it is. Technically, those 3 are the vectors, but I'm being sloppy in my notation. I need to get the VF by, already is, so straight plug and chug. 5.6 times 10 to the third plus, I'll write 2.23. I'm going to use my answer button, times 720. Did you get 7,206.1538, 7,210? I'll go to 3 sig figs. Did you use your answer button or did you use 2.23? So you typed more for less accuracy and an increased chance of error. You did more work. Oh, I don't understand you people. 710. So what was it? 7,210, not 710, 7,210 meters per second. About 7 kilometers a second. Fast-ish, but we get rockets going faster than that. What's C want me to find?
How far will it go?
Okay, you know what? I'm just going to go D equals question mark. I think I would choose, we got several options. I think I could use VF squared equals VI squared plus 2AD. Get the D by itself. I think I could use D equals bracket VI plus VF close bracket times T over T. I think I'm going to use D equals VI T plus a half AT squared because I got VI, T, and A sitting right there. The only problem is now, Kiana, I will use the 2.23 because I don't have it on my answer button anymore. Or I could quickly retype it if I wanted to be really, really accurate. I could retype part A into my calculator and store it. Nah. It's going to be 5.6 times 10 to the third times 720 plus 0.5 times 2.23 times 720. Don't forget the squared. There's one person that did forget the squared on their test a couple of times. Or they wrote it and didn't type it. Did you get 461 that? Or have I made a typo here? 4610016? What's less work, writing all that out with the zeros or writing it in scientific notation? I think I'm going to write this one in scientific notation. 4.26 times 10 to the, sorry, why did I say 26? 4.61 times 10 to the 6th. Yes? Am I right? Yeah, okay. That's fine. And that's meters, because that's what our equation gives us distance answers in. Okay. If this keeps up, what will the velocity of the spacecraft be after 48 minutes, George? Too slow. Deegan, what will the velocity of the spacecraft be after 48 minutes? Too slow. Alessio, what will the velocity? Stop typing, Alessio. If I say too slow, it means you already know the answer and you haven't been paying attention. What did I underline in part B? So if they shut off their engine, what's their velocity after 48 seconds, or 48 minutes, or 60 days, or 4 years? What does Newton's first tell us about how outer space works? Max? More specific as a number exactly.
I don't know.
Aiden.
It won't be 2.23.
Alessio. Riley. Nick. Owen. What? I heard someone start to, what? 7,210. Right? That's when they shut off the engines. And now Newton's first, and this is one of the nice things about outer space, the reason that we can travel in space at all is once we hit the speed that we want, once we're free of the Earth's gravitational pull, we can coast. Shut off the engine. How do you think Voyager got out past the edges of, our solar system and is exiting our solar system? It's coasting. When you see a rocket leaving the Earth, The vast, vast, vast majority of that fuel is to get it out of, here's the poetic way we describe it, Earth's gravity well. We'll talk about what that means later on this year. And into a stable orbit. Then to escape Earth, you need to go about 11,000 meters per second. But if you can get, actually it's 11,180, I think, 11,200 meters per second. Basically, if you go 11 kilometers per second plus a bit faster, once you do that, you can shut your engine off and coast to the edge of the universe. You'll get there. Maybe not very fast, but you've escaped Earth's gravity and Newton's first will kick in. If you want to go faster, fire your engines more to get an even bigger speed. That's all just kind of to help you understand what we can already do just with Newton's laws. Now let's dive into free body diagrams. FBDs for short. A free body diagram is a picture that represents the object that we're analyzing with a small dot. Any forces acting on the object are represented with arrows. Roughly to scale, and what I mean by roughly to scale, if you know that force A is bigger than force B, try and make force A arrow longer than force B arrow. Or if you know that force A is the same size as force B, make the arrows eyeball them about the same length, roughly to scale. You don't have to say, oh, I know it's twice as big, I'll make the line exactly twice as big. Eyeball it. We're going to use Newton's laws to figure out what forces are acting on the object. So here's 4 free body diagrams, although instead of I stole these from the internet because I'm terrible at graphics. Instead of representing the mass as a dot, they've represented the mass as a little square. Usually I'll just put a dot there. The net force is known for each situation, but the magnitudes of some of the missing forces are not known. We're going to analyze each situation, and we're going to determine the magnitude of the unknown forces. I'll zoom in. So it's going to go something like this. O and S, what's the net force as a number exactly? In A here, read it. 0. You know what that means? If my net force is 0, my forces must be, I'm looking for where that begins letter B. Balanced. Good. How big must force A be exactly then? Has to be. To the left. How big must force B be? Has to be. Now, this object could either be at rest, because that's 0 acceleration, or if we use our outer space analogy, it could be going in a straight line at steady speed. And that's why earlier, Max, when you said moving, I said, accelerating. That's all Newton's laws tell us about. They don't tell us whether it's moving or not. They just tell us whether it's accelerating or not, which is different. Aiden, if the net force is 900 newtons up, how big must C be magnitude? Yes. George, if the net force is 60 newtons to the left, okay, let's do left, right first. How big must D be so that we have a net force of 60 newtons to the left?
140.
I disagree.
Oh, wait. No. 20.
Good. Does this question mention any force up or down? So what must E be then? Exactly as a number. Yep. Now, again, Newton's first law says that there is exactly the same as if there was no vertical forces. It doesn't tell you what all the forces are. It just tells you if you're accelerating or not. You can make some assumptions. Ooh. Camille, how big must G be if we have a net force of 30 newtons to the right? Would 10 give me 30 to the right? How much do we have to the left already? So how much must I have to the right so that I end up with a net force of 30? Riley, I think I read your lips right. Did you say 50? Of course, you're going to say yes no matter what, right? Okay. You see how we did that, Camille? Now, Camille, Does this question say there's any up-down force at all? So how big must force F be compared to force H? Exactly. They must be so I'm going to say this has to equal H and this has to equal F. I can say that even though I don't know how big they are. That might come in handy if later on I'm trying to solve something that requires force F and I don't know it, but I happen to know how big force H is. I can put the same magnitude in. It'll work. We'll do that fairly often. Good. A book is at rest on a tabletop. Hey, your binders, for example. Yep. Go ahead. Actually, can you wait for this example and then go? A book is at rest on a tabletop. Look at your binder. A free body diagram would look like this. I always represent the mass with a dot. I'm going to zoom in. And then, Peniel, I'm going to try and teach you to go systematically. You're going to be tempted to rush to the confusing or weird or not understood force. Save it for last. So you're going to hear me say something about 1,000 times in the next few lessons. So what are the forces acting on this object? Get the obvious one. And the obvious one I'm talking about is the thing that's holding us down to the earth. Draw a little arrow pointing down and call that F. How about G for gravity? Now look at your binder. Is your binder sinking into the ground like quicksand? Is it flying into the air like Superman? In other words, is your binder accelerating? That means the forces must be, I'm looking for a word that starts with letter B. So there has to be a force pointing which way? Am I going to draw the arrow bigger, smaller, or roughly the same size as gravity? Eyeball it. That has to be there. Has to be there. What force is that? It's the table or the desk. I'm going to call it F desk. Go ahead now. But I just wanted you to see that concept. This is a weird concept because you're not used to an inanimate object applying a force, but it has to be. It must be. And if I go systematically, it kind of becomes obvious. But if you hadn't done gravity first, most of you would not have said, oh, the table's pushing up. But it is. Example 2 says, draw a free body diagram for the following masses hanging from a rope. So in the first situation, we're at rest. This is a job for a free body diagram. I'm going to represent the mass with a dot. What are the forces acting on that hanging mass? Get the obvious one. Draw gravity down. And we'll call that Fg. Ethan, is this mass accelerating down? No. Is it accelerating up? Because it says it's what? Well, that means if it's not accelerating, the forces must be, I'm looking for a word that starts with letter B. This diagram must be wrong because the forces are not balanced. Which way must I draw an arrow? How big? Same size roughly as the one down. What's exerting that force? The rope. We're going to give the force from a rope or a string or a cable a special name. We're going to call it tension. And so I'm going to call this F with a subscripted T for tension. Ethan, supposing I told you, oh, wait a minute. What is the acceleration due to gravity as a number, folks? Just as a number, as a magnitude. So if I wanted to find the force, I could go 12 times 9.8. The force of gravity down is 117.6 newtons. How big is tension in the rope then? Exactly as a number. Loud and proud. Has to be. Oh, what if this rope is going to snap at 100 newtons? I already know ahead of time, can't use this rope. Okay. Ooh, what if we're accelerating up? Which way? Up. This is a job for a free body diagram. What are the forces acting on this mass? Get the obvious one. Deegan, which way is this mass accelerating? I'm going to ask you the same question. I want you to say the same two-letter answer. I'm just going to phrase it differently. Which way must I have a bigger force pointing? Which way am I going to draw a longer arrow? I'll exaggerate it so it's obvious. This is why I said I'm doing roughly to scale. What I'll tend to do is exaggerate the differences so it just catches my eye when I look at it later on. I don't confuse myself. In this case, tension has to be bigger than 117.6. I know that. And in fact, I can actually solve for that a bit later because they gave me the acceleration. Next page. Today, we're going to introduce a couple of new forces to you. One I've already alluded to, gravity. One of the forces that you're most acquainted with is gravity. By the way, there are 4 fundamental forces in the universe. Tension doesn't really exist. Friction doesn't really exist. I'm going to be teaching you a bunch of forces that technically are combinations of quantum phenomena. We're just not going to dive down there all the time. So if you ask a physicist how many forces are there, they would say there's 4. There's what's called the strong force. That's what holds the nucleus together. You learned in Science 9 that like charges, remember the next word? Like charges, there's a word that starts with the letter R that you used, repel, okay? So if like charges propel, if protons are like charges, why don't all nuclei explode? Strong force. It's called the strong force. Okay? It glues the nucleus together. There's something called the weak force. That explains radioactivity. And I'm not going to dive into that, but that explains why atoms can decay and give off beta and alpha and gamma particles, all that stuff. The third one is electromagnetism. We used to think electricity and magnets were different, but we learned at the turn of the last century they're 2 sides of the same coin. And the fourth one is gravity. Those are the only 4 forces in the universe. Gravity is the weird one because gravity is weaker than weak. Although you think it's the strong one, that's only because you live on a big planet and it affects you. But gravity is hugely weak. So I'm going to be giving you a bunch of nonsense forces, but we'll pretend they're real because it makes the math easier. What's tension actually? It's the atomic bonds and the rope tugging on it. You know what? It's tension. Good enough. Okay. So the force of gravity is calculated as follows. F equals what? Except we'll use a lowercase g for the acceleration due to gravity. I think that's the second equation that I gave you on your green sheet in this unit, I think. Deegan can double check, yeah? It's F equals ma, and then right next to it, it says Fg. And then it says also that another word for gravity is what? No now. Wait, no now. Wait, no now. He hasn't figured the joke out yet. You're going to have to explain it to him, okay? He said wait. I said no now. Wait. Yeah, I know. It took a while. Little Doppler effect there, right? The rest of the class got the joke. There's the pause. And then Deegan gets the joke. Having said that, I'm going to be fussy in physics. If you're talking about mass, that's kilograms. If you're talking about weight, that's kilograms times 9.8. That's a unit of force. It's measured in newtons and not kilograms. That's probably a good test question. Weight is not mass. They're not the same thing. Your mass doesn't change anywhere in the universe. Your mass is the same on the moon or near a black hole. Your weight, the force of gravity, is what changes. So example 3 says, find the weight of a 35 kilogram object A on the Earth or B on the moon. I'm going to put a little A right there, draw a little line, and a B right there. How's that? Peniel, what's this question asking me to find? Find the no now. See, wait, no now. That's the joke. Okay. Find the weight, which is another word for force of gravity. So I'm going to write this. Fg equals, and over here I'm going to write Fg equals. And to calculate the force of gravity, that's mg. That's mg. But since we're on a different astronomical body, I'm going to put a little E for Earth, M for Moon. Peniel, in this question, how big is the mass that we're trying to calculate the weight of? I totally agree. So on the left, it's going to be 35 times, oh, what was the acceleration due to gravity on the Earth? Magnitude only. We don't care about direction. I can do this in my head. It's going to be 350, take away 7. Is it 343? Double check me. No? Yes? 343 newtons. What about on the moon? Well, what did I tell you that G was? I told you in part B, Peniel. What's G on the moon? Loud and proud. So it's going to be 35 times 1.6. You'll notice, does the mass change on the moon? No. What changes? Weight, which is different. That's the force of gravity. I can do this in my head as well. It's going to be 35 plus 7 plus 7 plus 7. It's going to be 35 plus 21. Is it 56? Newtons. So if you see the videos of the astronauts on the moon, the reason they were able to wear those bulky, heavy spacesuits is because on the moon, those suits weighed less. Same mass, different weight. Here's the key concept. Here's the whole thrust of this lesson. This is, if listing your data DFIC was what I gave you as your handy dandy tool in the last lesson, your tool in last unit, your tool in this unit is going to be a free body diagram and this here. To solve situations involving forces, we're going to use a little tug of war analogy. We're going to draw a free body diagram, carefully label all the forces, figure out any missing ones by using Newton's laws, and then we're going to decide which is the winning or strongest force. Pick up right here from where we left off because this is the key concept here. Get the stuff that you missed later. We're going to use our knowledge of physics to decide which way we're accelerating. That's the winning direction. And we're going to use the following equation. Winner minus loser equals F net. Remember those 3 or 4 square pictures we analyzed on the previous page? That's really what you were doing. You were looking at the bigger force and going bigger minus smaller. Winner minus loser. Oh, where F net is actually equal to MA. So what you're actually going to see me do is write winner minus loser equals MA. I'm going to save myself a step. And that's really, when I say F equals what, MA, what I really should be saying is F net equals MA. The overall combined net force. Example 4. Suppose the box is resting on ice and the following forces are acting on it. A says add any forces you think are missing, and B asks how fast will it accelerate? Okay, this is a job for a free body diagram. Now, how do I know that? There's multiple forces and they're wanting me to find an acceleration. Or they give me the acceleration and there's multiple forces and they want me to find one of the missing forces. Let's represent the box with a dot. What are the forces acting on this box? Get the obvious one. Go systematically. What's the obvious one? Yes. Now, I wrote Fg last time, but now that we know that the equation to calculate the force of gravity is little m, little g, you're often going to see me just write the equation and I'll save myself one step. Is this box sinking into the ice like quicksand? Is it flying to like Superman? So I know there has to be an arrow pointing up the same size. I'll call that F ice. The ice must be pushing up on it. And those cancel out, and because they cancel out, I can ignore them. Yay. What else? Well, the other two forces are from the picture. I have a 14 Newton force that way. I have a 6 Newton force that way. And Peniel, can you see I exaggerated the length so it's really obvious which one is the bigger force? Who's winning? Who's losing? So here's my force equation. Winner minus loser equals MA. And now we're going to use a modified version of Chiana's law. Chiana, how do I get the A by itself? How do I get the A by itself? Divide by, cross out the M, big fraction line, it goes there. So this is going to accelerate at 14, take away 6, divided by 3. Can I do that in my head? 14 take away 6 is 8 divided by 3. Sure, I can. 2.6 repeating? Yes? No? No? Yes? By the way, is this a fraction? Is there more than one thing on the top? So either brackets around the top or use your fancy schmancy fraction bar. Right? 2 points, so I'll go 2.67. Units for acceleration. By the way, as far as I'm concerned now, Ariana, it's also fair game for me to, instead of saying, here's all the forces, get the A by itself, give you the acceleration and the mass and ask you to find one of the mystery forces. Not a big extension. Example 5. Suppose the box below is sitting on a table and it's accelerating to the left at 3.2 meters per second squared. A says, add any forces you think are missing. B says, if Billy is pulling to the right with 24 newtons of force, how hard is Abe pulling to the left? This is a job for a free body diagram. How do I know? They want me to find an or they gave me an acceleration. There's more than one force, and they want me to find a mystery force. I'm going to represent this box with a dot. What are the forces acting on it? Get the obvious one.
Gravity.
Is this box sinking into the table like quicksand? Is it flying here like Superman? Mr. Dewick, will there ever be a... We'll get there, where eventually there's also vertical forces. But we'll get there. But for now, it seems to me that the table, I'll call that F-tab as an abbreviation for table, is pushing up with the same force that gravity is pulling down. Has to be Newton's first. It looks like I also have Billy pulling to the right. You know what? I'm going to use B for Billy and A for Abe. I'm going to go like this. FB equals 24 newtons. Am I going to draw Abe bigger, smaller, or the same length as Billy's?
Smaller.
Small, bigger. One of those was right.
Smaller.
How do you know Abe must be bigger? Which way are we accelerating? Which way must Newton's first be telling us we have an unbalanced larger force? To the left. But you got the wrong reason. Doesn't help. There's my free body diagram. When you get good at these, they'll take about a second. It's such good organization for a minimal amount of time and effort. They're a really good tool. Who's winning? Who's losing? Winner minus loser equals MA. Now you'll notice this time we made to the left positive because it made the math nicer. In the last unit, I would have let left be backwards and negative. Here, it's much nicer to do it this way. What am I trying to find? How would I get Abe by itself, FA by itself? How will I move the FB over? Deegan. Say that again? I disagree. What's the FB doing to the FA? So how will I move it over? Okay? Yeah, we're not trying to get A by, we're trying to get this, right? Plus it over? Yet another equation, don't memorize it. You okay with that, Ethan? Plus it over? All right. Have we got the FA by itself? Good. Plug and chug. Here we go. What's the mass? They told me in the picture. 5. What's A? They told me in the question and in the picture. Mr. Dewick, it's to the left. Shouldn't it be negative? We took care of all of that with our winner minus loser and free body diagram. So here in this unit, we won't be putting in negatives in for our accelerations. We'll take care of it in the setup. Plus 24. I can do this in my head. 5 times 3.2 is 16 plus 24. 40? Units. It's a force. Newtons. Next page. I like example 6. I like example 6. Example 6 is a nice question. I like example 7. I like example 7. Example 7 is a nice question. I probably like example 8 too if it includes a rope and a mass and tension. I can't remember. Okay. O and A, what does number 6 want me to find? Tension, like you're feeling right now? Little tension? Okay. This is a job for a free body diagram. How do I know that? I know that there's gravity in this question, that's one force, and they're asking about tension, that's 2 forces, and there's an acceleration. I'm not just going to try going F equals ma, I got to set this up properly. So I'm going to do the free body diagram right here. Oh, and what are the forces acting on it? Get the obvious one. So draw an arrow pointing down, and we'll call that mg, because that's how you calculate the force of gravity. What else? Which way does this question say the box is accelerating? Which way does Newton's first say that I must have a bigger, larger, unbalanced force pointing? Longer arrow pointing up. I'll exaggerate it. What force is that? Well, it's got to be the rope. What do we call the force from the rope, Owen? What you're feeling right now? There you go. See the setup? This is why I said to you earlier, I can't give you every single equation on your sheet. You're going to derive it because if it's down, it's a different equation. I'm not going to try and come up with a situation. Oh, and which way are we accelerating? Who's winning? Good. Who's the loser? Deegan, I said, who's the loser? And he looked at you. No, I said, who's the loser? And he stared right at you. Wow. Deegan, Bonson Park, 3 o'clock. If I'm not there, just start without me. You show him who will lose it, right? Fine, Owen. Which is the losing force in this equation? Yep, so minus mg. What does winner minus loser always equal? ma. If this question wanted me to find the acceleration, Kiana, how would I get the A by itself if that's what they wanted? Bam. Does this question want me to find the acceleration? No, it wants me to find the tension. How will I get Ft by itself? Oh, and how will I move this minus mg over to the other side? Yep. So if I hear you correctly, you're telling me that tension equals ma plus mg. Have we got the Ft by itself? So yes. Let's plug and chug. What's the mass? It's in the picture, Owen. What's A? They told me in the picture. 2 plus 12. I'm not going to put in negative 9.8. I'm just going to put in 9.8. I took care of the negatives and positives with my winner minus loser shtick. I think I can do that in my head. It's going to be 12 times 11.8. What's that going to be? It's going to be 12 times 11, which is 132. 12 times 8 is 96. So it's going to be 132 plus 9.6. 141.6. I might be wrong. Yeah? There you go. I'll call it 142 newtons, even though you all know that I went to 4 sig figs in my head. Oh, and it's a force, newtons. If it was an acceleration, meters per second squared. And by the way, I guess I could also have you find a mass. If I told you all the other information, I could say how many kilograms is in this situation for this to work. That's later. Cool. Awesome. Nicholas, what's example 7 want me to find? Like you're feeling right now? Shut up. This is a job for a free body diagram. What are the forces acting on this object? Get the obvious one, Nick. Acceleration is not a force. What are the forces acting on this object? Get the obvious one. I'm looking for a word that starts with the letter G. That's always going to be the response to when I say get the obvious one. Unless we're in outer space, but we haven't got there yet. So get the obvious one. Which way? Is that it? The only way that would be it is if we were in free fall. We're not. Which way are we accelerating? Which way is my larger winning force pointing? So there's going to be a force pointing up, the rope, but it's going to be smaller than gravity. I'll really exaggerate it. I think that's fairly obvious that one's bigger than the other. And that's what I meant by roughly to scale, because this is not to scale, but mixture biggers are biggers and smallers are smallers and equals are equals. Who's winning? mg, winner, minus, who's the loser? Owen! You didn't see it. I said, who's the loser? And he looked at you. Oh. The disrespect in this classroom is amazing. Wow. He's got the shades. He thinks he's so cool. Owen, Bonson Park, 3 o'clock. You teach him who's cool, right? Fine. Who's the losing force? What does winner minus loser always equal? MA. There's something I don't like right now about this equation. It's what? I don't like the minus sign in front of the tension. In fact, that is giving me tension. Wait a minute. Couldn't I plus it to that side? And now it's positive. I'm positive. But that would give me MA plus FT. And that doesn't get the FT by itself. How would I move the MA over? So here's something that a student a few years ago, because we do this so often, I had a student nickname this the Swappy Dance, she called it. She said, Mr. Dewick, when the thing that I want has a minus in front of it, draw an arrow moving it to that side. At the same time, draw an arrow down here. She put a plus and a minus. And she said, hey, the MG drops down like a domino. Yes? You would minus the MA over here, and then that equals FT, although she said, Mr. Dewick, we're used to putting the thing by itself over there. She called this the Swappy Dance. And so you're going to hear, we're going to do that one fairly often, where we want to just swap two objects, plussing the one over if it's negative, and minusing the other one over if it's positive. It's going to be M, 12, G, positive 9.8. I took care of the negative in my winner minus loser stick. Minus 12 times 4.2. Can I do that one in my head? 5 points. It can be 12 times 5.6, so it's going to be 60 plus 7 point. Is it 67.2?
Yeah.
Okay. Well, we were accelerating up. We were accelerating down. What else can I do with this mass hanging from a rope? And then we'll build with other forces as well. But we typically start with something like this. Good question. Example 8. Alessio, what does example 8 want me to find? Like you're feeling right now, this is a job for a free body diagram. What are the forces acting on it, Alessio? Get the obvious one. What else? Bigger, smaller, or the same size as mg? There's two words we should have underlined, either mentally or actually. Can anybody see the two-word phrase that we should have caught? Kiana, loud and proud. What? If we're at a constant speed, what's my acceleration as a number exactly? If A equals 0, Newton's first says the forces are, I'm looking for a word that starts. So I'll ask you again, the arrow that I draw pointing up, bigger, smaller, or the same size as mg? Very good. And once you've done that, put your pencil down for 1 second. Don't write this next bit down, look up. So you could go like this. You could say, well, I'm moving up, so I'll pretend tension's the winner. It's actually a tie. And so you could go winner minus loser equals MA. But what's A as a number exactly, Kiana? 0. So what would M times 0 be? And so this would become a 0. And then how would I get the FT by itself? How would I move the MG over? And so you would end up with that. Is that okay? Pick your pencils up. Or you could say it's a tie because A is 0. The forces are balanced. But I just did kind of a mathematical proof as to why that works. There's your equation. Write that down. Mr. Dewick, what do I do with that 3.8? I threw that in there totally to suck you in. To see if you would stick that in for an acceleration, even though it's a meters per second, not a meters per second squared, and so it can't go into an acceleration. What's M? What's G? 9.8, not negative. We took care of that in our winner minus loser stick. So the tension in the rope is going to be 12 times 9.8. It's going to be 120, take away 2.4. 117.6, I think. I'm wrong?
No.
Oh, Deegan shook his head. Am I right? 117.6? $118 if you go to 3 sig figs. Okay. So far, I've been giving you the acceleration and saying find a missing force. Or I can give you all the forces and say find the acceleration. I like example 9, I like example 9. Example 9 is a nice question. As is example 8 and example 7 and example 6. Although, to be honest, they're a little easy. We're going to get more complicated, but we'll get there. We'll build to it. We'll build to it. Prabnur, what's example 9 want me to find? I think the tension is 98. What? Loud and proud? Okay. Now, if this was a week ago, you would have thought A equals question mark. VI, is there a VI or a VF? Or we're in forces. This is a job for a free body diagram. What are the forces acting on this? Get the obvious one. Yep. What else? Yep. Bigger, smaller, or the same size as mg? You know what? I don't know because they didn't tell me which way we're accelerating. Wait a minute. Get your calculator out. I can calculate mg. What's m as a number? 12. What's g? 9.8. Can you go 12 times 9.8 on your calculator, please? Okay. How big is tension exactly according to this question? How big is gravity? Which arrow is going to be bigger? I'll draw tension shorter. See how I put that together? Yes? Okay. Now look at your free body diagram. Who's winning? Who's losing? So winner minus loser. What does winner minus loser always equal? MA. What did you tell me this question was asking me to find? Oh, Kiana's law. How would I get the A by itself? I'm lazy. I don't want to rewrite this, but I want to be organized. Riley, I would do this. There, I've showed my work. Duick will figure out what I was getting at. So I think the acceleration is going to be M, 12, G, 9.8, minus 98. I don't need to multiply that by anything. That is the tension. All divided by what? Is that a fraction? Probably more than one thing on the top, brackets around the top, or fraction button. You want me to do that in my head? Maybe. It's going to be 117.6 minus 98. So 117.6 minus 100 would be 17.6 minus 2, 15 divided by 12. It's going to be around 1.2. I don't know. 6? I was off by that much? No, I don't. And honestly, I'm enough of a nerd that I still enjoy getting the answer. I do get that tiny nerdy adrenaline rush of, haha, I got it right, right? It's why I give you the answers in your homework whenever possible, because I do think, oh, I got the right answer. Yay, that is a little bit of I'm enough of a nerd to enjoy that. And this is acceleration, so units, Prebner? Yep. Okay. So what's your equation for this whole unit? Winner minus loser equals MA. That's the template, but then you'll just have to derive the rest because there's just no way I can come up with every single situation. Ain't gonna happen. Mr. Duick jumps out of a plane. Wearing my shirt.
Oh,
Yeah, my students bought me this a few years ago, so I figured I'd wear it today since it fit in. Once he pulls his parachute, air drag has a force of 745 newtons. Now we can start looking a little bit at air resistance. Still not properly, but we can look at it in snapshots. Cool. Aiden, what's number 10 want me to find? Is there air drag force in this question? Is there also the obvious one? Yes. Is there more than one force? This is a job for a free body diagram. What are the forces acting on Mr. Duick? Get the obvious one. Which way? What else? Air drag, which way? Up. Bigger, smaller, or the same size as mg? Good. Yeah, you have to crunch it this time. So what? Oh, hang on. Stop. What's 9.8 really close to? 92 times 10. Air drag's roughly 920. Bigger. I'll call it F air, or you could call it F drag. Who's winning? Loser minus mg equals ma. Divide by m, yes? To get the a by itself. Kiana's law, modified. So, right when I jumped, before air resistance kicked in, I would have been accelerating at 9.8 meters per second squared because air resistance would have been 0. Sorry. I did this totally backwards, folks. mg is larger, isn't it?
yeah.
Wow, Duick, did you botch that? I'm sorry, folks. We did the math and somehow I came to the wrong conclusion. Wow. So it's mg minus f air. By the way, suppose we had done that. So here's a little rule of thumb for you. If you get a negative acceleration when you're using this method, you pick the wrong winner, go back and check your directions. So there is, in this unit, if you ever solve for A and get a negative, don't panic, but you've made a mistake somewhere. My brain was trying to do this in my head and I was getting a negative. Wait a minute. mg, so 92 times 9.8 minus 745 all over 92. This one I can't do in my head. Is it a fraction? Brackets around the top. Oh, typo, Mr. Do It. You're in a slump. Got to recover. Do you get 1.7?
Yes.
Okay. Look up. Don't write this down. Take a look at this equation right here. You've all, I hope, stuck your hand out of the window of a moving car. As you speed up, what happens to air resistance? So as I accelerate down, what happens to the air resistance on me? This would get bigger and bigger and bigger until eventually, instead of 745, it would exactly equal gravity. And this acceleration would be then what as a number? That's terminal velocity. It doesn't mean that I'm flying. It just means I've stopped accelerating. But if I hit the ground at that speed, it would be terminal. Then, when I open my parachute, we'll look at that in another question. Caleb jumps from a 19.5 meter high cliff into a lake. If we assume his mass is 65 kilograms, A, find how long until he hits the water, ignore air drag. What's this question asking me to find? Oh, this is not a job for a free body diagram yet. I think I'm going to go T equals question mark. Okay? Oh, what else do I know? What's D? I'll give you a hint. It's not 19.5. Negative. Because Caleb's ending up below from where he started. What else do I know? Oh, if you're cliff jumping, what's VI? You don't jump down, or you might jump up a tiny bit, but typically you're jumping outwards. Vertically, your velocity is pretty close to zero. What else do I know? Now, Owen said mass, and I do know that, but did we use mass at all in these equations here?
No.
I'm going to hold off on that. Oh, do I know the acceleration? And now I'm going to include the negative, because in our kinematics unit, it was easier to let down be negative. Here, we got so many forces, it's easier to let positive be whatever makes the math nice. Which equation? Why'd you waste my time? Which equation? There was this equation, this particular situation, finding time when you knew how high the cliff was on your test. This was one a few people struggled with. We'll go through it. It's also why I stuck it back on here. Alessio does the 0.5, that's fine. How would I get Deegan the T by itself? How will I move the A over? I agree. How would I move that 2 on the bottom over? That gives me a T squared. There was 3 or 4 of you that forgot the square root on this question on the test. Cross that out, draw the square root, and or you did this. You did that wonderfully, and then you went what'd you forget to write? So you'll actually notice, because that's such a common error. because you're so relieved you got all the numbers in the right place. You'll notice most of the time I've taught myself I do the square root first so I don't forget, because I have in the past. It's going to be a little under 2 seconds, about 1.9. Is it 2? By the way, 19.5, really close to 20, divided by 10. This is really close to 2 times 2. This is really close to the square root of 4, which is going to be really close to 2. So if you're wondering how I did that one, I estimated it, but I knew I'd be pretty close. Times negative 19.5 divided by negative 9.8. Square root of that. I typed that wrong, didn't I? 98, Mr. Duke. Negative 9.8. Square root of that. Yeah, 1.99, 2.0. You know, I'll go to 3 sig figs, 1.99. Basically, if you're cliff jumping from 20 meters, you're in this air for 2 seconds. What's B asking me to find?
Yeah.
Okay. Put your pencils down and look up. We're grown-ups now, as far as I'm concerned. If I was being careful on a test, I might use this one. Because they gave me VI, I know A, I know D. What did I just find in part A? Time. I'm going to now say I'm confident enough to use an answer to find an answer if it's lazier in the homework. I would use VF equals VI plus AT. Oh, what's VI, Deegan? So I would use VF equals AT, especially because I have time sitting on my answer button. And Kiana, I'm going to use my answer button because it's less typing, less work, and more accurate. Kiana, what's A? T. All right, 1.99. I'll use my answer button. And the nice thing with this equation is if V is negative, it will give me the negative. If I use the VF squared one, I always have to ask if I take the square root, do I want the positive answer or the negative answer? So this lets me kind of be a little more mechanical. So I'm going to say now, for the remainder of the year, if you want to use an answer to find an answer because it's just less work, as long as you know your first answer is right, knock yourself out. Answer button. Do you get negative 19.5? In meters per second. In an odd coincidence, if you jump from 19.5 meters of height, you'll hit the ground at 19.5 meters per second, roughly. 2 seconds of free fall. That's a fluke. Don't read anything special into that, but it's just kind of nice. If Caleb's feet just barely touch the bottom of the lake, which has a depth of 2.5 meters, what was his average acceleration while he was in the water? Now they're asking me to find A. I started to think maybe free body diagram, but did they give me a distance? Maybe I can still solve this using kinematics. Talk to me. Yeah. Oh, so Max, did I hand up? Yeah. What's D? Now, you could say that D is technically below him. We could let D be negative. That would give us a positive acceleration up. Or, because I know he's slowing down in the water, I could let this be positive. We'll get a negative acceleration because he's slowing down in the water, which is up. I don't care. Since you said 2.5, I'll go 2.5. What else? What's VI? It's not 19.5. Oh, okay. What else do I know? By the way, the fact that I know two things, this suggests, I probably don't need a free body diagram or anything fancy-schmancy. If he just barely touches the bottom, that was my way of saying to you that his foot goes slowing down, slowing down, slowing down, slowing down. Doink! VF is? Yeah. Question, Alessio? Oh, you're going to say that? Okay, I didn't tell you to get your green sheets out, so we're kind of going from memory. Which one has an A, a D, a VI, and a VF in it? Squared, V equals VI squared plus 2AD. So let me think here. The VF squared would drop down like a domino. Minus VI squared all over 2D. Okay. Look up. Common mistake on the test number, whatever I'm on. I saw several people do that. That's not an equation. I don't know where you're getting that. There's squareds on there. One person did that every single time they used this equation. And if you don't think that dominoed through and cost them some marks. And the other one I saw was this. That's not an equation. Never given you that. So it's going to be 0 squared minus negative 19.5 squared all over 2. Max, look up, trick of the trade. This negative in the brackets, when I square it, will it vanish? Then I'm not even going to bother typing it on my calculator because it's extra typing, and then I'd have to remember, does it go on the brackets? You know what? It's irrelevant because it's going to vanish, so I'm going to type bracket 0 squared minus 19.5 squared divided by 2 times 2.5. I get negative 76.05, meaning slowing down, or if I'd let the D be negative, I'd get a positive answer, which would mean in the opposite of negative direction, up, which is slowing down. I'll call it negative 76.1. Yeah, about 7.5 Gs. This is owie. Well, although, see, it all depends. What would really happen is as soon as you started to hit the bottom quickly, because you've all played on playgrounds as toddlers, you have built a reflex in. Almost certainly, without even thinking about it, you would just bend your knees. And what you're really doing is increasing this distance. You're letting your body travel further, maybe even half a meter further, can dramatically change this, right? Although Caleb, he played basketball for us, he wasn't that smart. He might have just landed wrong. D. D. What's the net force that the water exerted on him? No. If I was doing this from scratch, yes. But what did I find in part C? You know what? F net equals MA. I could go winner minus loser, and then I would have included the force of gravity. I could do the whole schmear. I think I already did. What was the mass? I forget. And now we're using the mass finally, Owen. Was it 65? And A was, all right, 76 point, well, you know what, 05. Since it's sitting on my calculator, I'll write that. Use my answer button. I'm ignoring the negative, but if you ask me for a direction, the water is pushing which way on him? Up. (4,940 newtons. Now, if we're going to be really, really technical here, Riley, I suspect in real life this acceleration is not constant. I think water, much like air resistance, water resistance, the faster you're traveling, the bigger the force. The maximum G's are right impact. As you slow down and get towards the bottom, then it's comfortable and nice. But we can't handle the changing acceleration. So we're finding an average, technically. Almost done. For a cyclist moving to the right at a constant speed while pedaling. There's the cyclist. What are the forces acting on this cyclist? Get the obvious one. Is this cyclist sinking into the pavement like quicksand? Are they flying you like Superman? So that means that vertically the forces must be, I'm looking for where it begins, letter B, balanced. So I'm missing something. Yes? Same size. And that would be F, I don't know, pavement. By the way, in the next lesson, we're going to give that force that the ground exerts or the table exerts or any surface exerts a special name. Just haven't done it yet. What else? Oh, that's good. Let's suppose you're biking really fast. What do you feel on you when you're biking really fast? Okay. Why can't this be right? So, where else must there be an arrow pointing? Bigger, smaller, or the same size as F air? And this would be your legs, like the pedaling force. It's more complicated than that because actually you apply a rotational force to the pedals, which apply a force to the chain, which apply a force to the... But for now, let's just say it's your legs. What if I want to go faster? What if I'm in a race and I can't pedal any faster? Which other force can I affect in here? We've just explained the Tour de France pose. Right? There's a reason why they're all hunched over like that. They're minimizing. They practiced in wind tunnels, and they've found how their body with their bike, they've memorized the pose that they have to hold, which minimizes this, and then you do have an unbalanced force forwards and get to accelerate a bit more to a higher top speed. Yep. Even to the point of, you'll see in Olympic cycling when they do it in the arena, they don't have spokes, they have a solid hub because the small spokes have some air resistance. They've looked at it all, but we can understand why they've done it now. I like example 13. I like example 13. Example 13 is a nice question. Draw a free body diagram for an inline skater who is dragging the toe of one skate in order to slow down and stop. Okay. This is a job for a free body diagram. What are the forces acting on the skater? Peniel, get the obvious one. Thank you, Peniel. That was amazing. Your lips didn't even move. Is the skater sinking into the ground like quicksand? Flying you like Superman. So the ground is pushing up, same size as mg. Inline skater, I'm talking rollerblade. TM. So I think rollerblade is actually trademarked. What else? Sorry? How do you know there's an arrow pointing to the left? Which means if they're slowing down, which way are they accelerating? What force is that? Well, if I'm going to be fussy, it's friction, because that's what when you're dragging your foot. What else? Is inertia a force? What else? Is speed a force? Is velocity a force? Is velocity measured in newtons? Air resistance would technically be that way, but we're going to ignore air resistance. What were you suggesting? Is there a rope? So you're feeling tension, but there's no tension in this question. I can't hear you. What? Is weight a force? Well, that's for acceleration's not a force. I'm not going to put acceleration on my free body diagram. Weight I have right there. Gravity. Got it already.
Dragging a pole.
No, we're not constant speed. So here's my question. Look at your free body diagram. Does that allow this person to slow down? This is it. There is no force pointing forwards. And this is a very difficult one. This is why when you said moving at the beginning of class, I jumped on you right away. Newton's laws don't tell us anything about how we're moving. They only tell us how we're accelerating. Which way are we accelerating? To the left. That works. There's no force pushing them forwards. Their own inertia, Newton's first law, has kicked in, and that's why they're traveling forwards. We have to apply a backwards force to overcome Newton's first, but there is no force pushing them forwards. Inertia is not a force, it's mass. Acceleration is not a force. Velocity is not a force. This is the free body diagram for a moving object coming to a stop. And it's very counterintuitive because, they want to put... In fact, I was at a physics conference where a physics teacher who was teaching out of subject, they didn't have a good physics background, they had an arrow pointing forward and they taught their kid that there was a force pointing forward, and I had to gently correct them and say, no, there's not. There can't be. There isn't. Don't need it. Air resistance, if you wanted to add one more, but we're doing our ignore air resistance.
It was an early April Fool's.
Number one. So number one, you can do a whole bunch of little free body diagrams. You might be able to fit it on this piece of paper. I would recommend a separate piece of paper. So you're finding the tension, and I'm giving you a bunch of different situations. The mass is 2 kilograms. In one situation, we're accelerating, so we're at 0 meters per second squared. We're accelerating 6 meters per second squared up or down or down or up or down. See if you can solve for tension there. I put the answers in brackets. Number 2 is good. Number 2 is a bit tricky, but I'm going to see if you can figure it out. Number 3, I'm going to skip. Normally, I would do it as an intro to Physics 12. One of the things we do a lot in Physics 12 is I'll give you a theoretical question with no numbers and just ask you to tell me what's going on. So here, the force is F, not 12, F. And if the first block accelerates at A, what would a block of 2m accelerate at? That's a Physics 12. We start doing things algebraically. 4 is good. 5 is good. You can skip 6. 7 is good. 8 is good. 9 is so easy that it's tough. Your hint is you don't need to use a free body diagram until D. You can solve everything else with kinematics. Ten is good. And I just realized there's 4 situations, but the graphic got wrecked. So I guess I'm skipping 11 because there's only one picture there. 12 and 13 and 14. That's a lot of practice, I know. Put your pencils down, look up.